In this lecture, we are going to talk about a new area altogether, and that is known as thermography. By now, we have a knowledge of how vibration can be used for machinery health monitoring or condition monitoring. And then in the previous classes, you saw how motor current signature analysis can be used to find out faults in mechanical systems being driven by electrical machines, and also find out the faults in the electrical machines themselves. But today, we will discuss on a new topic called thermography, essentially by the measure of thermal energy emitted from a body. As you know, any machine, it generates heat because of friction between the moving parts sliding over one another. There will be a lot of heat generation, and this heat generation increases with the frictional force, and frictional force will increase if the normal forces onto the surfaces increase. Now, this normal force could increase because of a defect. So, thermal imaging gives us a easy clue as to that an abnormal excessive force is coming onto this machine. Particularly, for example, I will just give you an example here. I have two machines, and then there is a strong bit of misalignment between these two shafts. So, there will be a push pull force onto the surface of these bearings. So, what happens? The frictional force, whatever be the direction, okay, it is normal to the direction of the normal force. Now, if this friction force increases, there will be a lot of heat generation. Okay, if heat generation is there, obviously the temperature is going to rise. So, indirectly by measuring the rise in temperature, we can say that an abnormal force has happened. Well, how can we measure temperature? We know if we use thermocouple, if we use a resistance temperature detector, RTD, etc., we can measure the temperature of any surface. But mind you, these are contacting surfaces, these are contact type sensors. So, we have to embed these sensors in the area where we are going to measure the temperature. Rather, there is another method by which we can measure the temperature is, because the energy will be radiated, thermal energy will be radiated. So, if we can somehow measure this radiated energy, we can get a clue as to what is the surface temperature, and that is essentially what we are going to talk about in today's lecture on thermography. So, the principle of thermography is bodies actually give out infrared radiations. These are electromagnetic radiations, like we have the visible light, anywhere from 4000 to 7000 angstroms is the wavelength. And by the way, this visible light or electromagnetic waves travel at the speed of light 3 × 10⁸ meters per second. Okay, speed of and later on we will see the entire spectrum. So, depending on the frequency, C is equal to, depending on the frequency of the wavelength, we can classify as short wavelength, long wavelength, and so on. So, if wavelength is high, the frequency is low, and wavelength is short, the frequency is high. So, if we talk about TV signals, radio signals, gamma rays, X-rays, ultraviolet rays, infrared, bodies always give out infrared radiation, and this infrared energy is dependent on the absolute surface temperature. You will recall there is a nice law in heat transfer the StefanBoltzmann law, which we will discuss in later on. And of course, this infrared energy is dependent on the surface emissivity, and there are certain special types of semiconductors on which, if this infrared energy is incident, they will develop a voltage. Okay, so that is essentially the principle behind thermography. So, if I have a screen, okay, onto which infrared radiations are focused, and they are pixel by pixel, each pixel, okay, and they will generate a voltage proportional to the temperature of the body, surface temperature. So, if the body is hot, you can have a different voltage, and then you can color image them. So, it is only because of this particular semiconductor devices. So, basically I have a body which is giving out infrared radiations. So, this depends on its surface emissivity. I have some optical systems which will focus all this into a screen which is made out of a semiconductor device, and this screen looks like this, will give you a voltage which could be through a software you can get an image which could be color coded. So, the body's temperature you will get. So, this is essentially how the principle the thermography principle works, and we will see what sort of body conditions is important, how do we estimate IR, emissivity, how do we calibrate this, and what kind of camera system we require to get an image. And the practical applications of thermography are tremendous, because the ease at which you can measure, because this can be at large distances, and that is the essential advantage of thermography. Large distances, and they are non-contact. Imagine you have in the last class I was just mentioning about condition mounting of switch gears. Imagine you have a large transmission tower, okay, and it is carrying a conductor, okay, with a switch gear, and some sort of contact it has to make. Of course, there are insulators, I am not going to talk about them. Suppose there is a loose contact. So, with loose contact there will be a lot of sparking, and there will be heat generation. So, you can be standing here on the ground, and this could be maybe 40 meters from the ground. So, you could always shoot an IR beam and hold a camera, IR camera, and measure this place's temperature, and if it is high than the other transmission towers, or it is higher than the ambient, a loose contact is occurred. Otherwise, imagine how do you detect such loose contacts? You will see a lot of voltage drops, etc. So, this is one typical advantage of IR cameras, and same is true for windmills. Suppose we have a windmill wherein we have a gearbox mounted, okay, very high. Again, this is maybe 50 meters from the ground. So, if somebody was to make a contact type measurement, one has to climb up the stairs to go up to the gearbox, but rather you can shoot from an IR. In fact, there have been cases where people shoot IR cameras from helicopters. Okay. To monitor the temperature of a machine. Okay. So infrared thermography is defined is the science of thermal acquisition and analysis of thermal information from non-contact thermal imaging device. It is non-contact. So, you all know, this is just to recap, the amount of heat in an object is the total kinetic energy of the molecules that composes it, joules, and temperature is a measure of the average speed of the molecules and atoms that makes up this substance. Okay. So, temperature defines the state an object is in relative to other objects. So, temperature is an indicator of energy, though it is not a form of energy. So, temperature will rise and fall as energy in an object increase and decrease. It is a consequence of more or less energy. So, temperature of the objects will tell us how easy it is to give away heat to others. Okay. Somebody at a higher temperature will obviously heat energy will flow from a high temperature body to a low temperature body. Okay. But if they are at equilibrium, they all will be same. So, to see any momentarily rise in temperatures or a rise in temperature above the normal, we can use IR thermography. So, all the modes of heat transfer does work. The direction of heat heat will spontaneously flow from hotter to colder, thereby transferring heat from one body to another. So, temperature defines the existence of heat, and if there is a temperature difference, there will be a heat flow. So, basic mode of heat transfer are these three modes. Heat transfer by emission and absorption of thermal radiation is called radiative heat transfer, and this is what we are going to focus on. So, this thermal radiation is a form of electromagnetic radiation. Thermal radiation will easily pass through most gases, but will pass with difficulty or be blocked by most liquids and solids. So, objects will emit thermal radiation as a consequence of their temperature. So, since all objects have a temperature, all objects will emit thermal radiation. The higher the temperature, the more thermal radiation will be emitted. So, our objective is to measure this infrared emitted radiative thermal energy by a system which is usually this thermal imaging camera, which essentially has a semiconductor device onto which this thermal energy is focused, and this thermal semiconductor device on a pixel to pixel basis is going to give us a proportional voltage, and through the appropriate software we could have a 2D image wherein we can have a color image of the body whose temperature is being measured. So, heat transfer is by emission and absorption. Both objects emit and absorb radiation. So, there is no heat transfer is the difference between the two. Now, I just mentioned about this infrared. So, the electromagnetic spectrum, if you see at the high frequencies, we have very low wavelengths, okay, and then we have relatively high wavelengths and the frequencies are lower relatively. So, beyond just after the visible range, we have what is known as the narrow infrared region, where is very easily this infrared energy can influence a semiconductor. Some of these energies and these waves have very high power, and they are used for penetrating metals, X-rays or penetrating solid devices, where these cannot. Okay. So, depending on the frequency, the intensity of this energy can be calculated, and infrareds are that way not harmful, okay, and they can be used to measure the temperature of a body. We will see how. So, infrared this is the typical reason wherein infrared in terms of the micrometers you can say from 2 to about 12 micrometers is the wavelength of infrared waves. So, thermal radiation occurs in part of the electromagnetic radiation that begins somewhere within the UV band and continues throughout all of the visible infrared wavelengths, wavebands. So, visible is about 4000 to 7000 angstrom, near infrared about 10,000 angstrom, okay, and then short wavelength, long wavelength and so on. So, when an incident energy is striking a body, okay, from it will absorb something, it will reflect and it will transmit. So, this emission is this radiation that leads the surface regardless of its source. So, we are trying to measure this emission. So, excitant radiation is the total radiation from a target. A certain proportion will be emitted from the object itself, reflected from a source in front of the object, transmitted a source from behind the object. So, total energy is nothing but a combination of emitted, reflected and transmitted. So, this camera, this is a typically a handheld infrared camera which is being held. Okay. So, an object is emitting infrared radiations and we can measure it. So, this scientific law which I just mentioned before relates temperature to the radiative energy and it tells us how much radiation a black body at a certain temperature will emit. And all of you perhaps will recall from your high school physics that this is called the StefanBoltzmann Law. And the StefanBoltzmann Law states that the total energy radiated per unit surface area of a black body unit time is directly proportional to the fourth power of the black body's absolute temperature, capital T. So, this energy W black body is nothing but where T is 273.16 plus T in degree Celsius, whole thing in T is in Kelvin. And this is an universal constant, that is StefanBoltzmann constant. So, but this black body is something very theoretical, but we have a real body where the emissivity is not equal to 1. So, then it will give less emission or radiation in comparison to black body, and StefanBoltzmann for real bodies will be this. Okay. So, we see this for the real body. W real body is nothing but surface emissivity times Boltzmann constant. I have denoted this. Okay. In some book you will see the symbol this. Okay. So, the idea is how do I find out the emissivity of a real body? Okay. So, one which we will talk about emissivity. So, emissivity obviously will be nothing but it is the ratio of radiation emitted by a real body compared to the radiation emitted by a black body at the same temperature and same wavelength. So, IR cameras are calibrated to black bodies, so only black body radiation can be converted to temperature. So, hence we must compensate for real body by the following factors: emissivity temperature, reflected temperature, emissivity, reflected temperature, atmospheric temperature, humidity, so on. So, we have to calculate and compensate for the real body. Okay. So, we will see how it is done. So, if the bodies are in the same temperature, there will be no color contrast, because there is no temperature difference. So, coming back to this emissivity, thermal and electrical insulators are excellent emitters. So, measurement is not a problem. Woods, rubber, plastic, PVC, soil, paper, painted surface, building material, porcelain, concrete, they are all having a high emissivity, and then we can use this to measure the surface temperature by IR. But metals are poor emitters unless heavily oxidized. So, emissivity is rarely superior to greater than 0.025, like all these metals or any shiny surfaces. So, that is what we have to be careful about, and in one of the examples I will show you how this is taken care of. So, some of the measurement rule is get a good image first by this focusing system, and then target must cover the spot. Do not aim beyond this, so that, and try to measure in a high emissivity and make sure that your body reflection does not come onto you. So, capturing an image is freeze it. You have to know about the temperature range, the focusing and image composition. You should not be far away or too close to the target. Your distance from the object is such that it covers the critical points you want to cover. Reflected apparent temperature is the apparent temperature of bodies that result in radiation that is reflected by the target and into the camera. So, we have to be careful about this. So, measuring reflected temperature, make sure that there is a reflecting, okay, what is reflecting on your target, set the emissivity to 1 and distance to 0, put a box with average temperature measurement, note the temperature, this is your T reference. And measuring emissivity, select a sample, put a piece of electrical tape with known emissivity, hence heat the sample, focus and note the temperature tape, and move your measurement function to a sample surface, change the emittivity and note the emissivity. This is a very simple way to do it. I will explain you how. I will have a surface, okay, whose temperature is known to me, maybe by a thermocouple. So, I will put some sort of a patch and focus there and measure through. I do not know the emissivity, I will measure through this and get a temperature. Okay. So, I will vary this emissivity till I get this T equal to the T reference. Okay. So, this is how very easily you can know the emissivity of an unknown surface, or many times you can go to the handbooks and see the emissivity of different surfaces. Okay. Now, I will show you some typical examples wherein in a color code you can see typical measurements of this infrared thermal imaging cameras. So, this is an electrical switch gear wherein some loose contact is there and is high up from the ground. So, we can have a thermal imaging camera and you can see the hot spots being measured by such thermal imaging camera while in operation. So, you know there is something happening here, this temperature is very high. Okay. Then later on you can go ahead and make some diagnostic measures as to how to reduce that. A motor, electrical motor, okay, driving some unit, there is a high temperature here, close to 200 degrees Celsius. Very easily we can measure from a distance that something is wrong at this end of the electrical motor. Okay. In petrochemical, if there is a variation in the temperature, you can see in any applications what the temperature is. Application in steel mills, rolling mills, we can measure through infrared temperatures. With some of these IR cameras available in the market, we can measure around 800 degrees Celsius with an accuracy of 0.1 degrees Celsius. Imagine, this is very powerful in the sense, any place you want to measure, you can very easily do it. I will give you another example wherein electrical control panel. So very quickly you would like to know, because you just have some few switches. So, and there are lot of conductors, and then maze of conductors, and these black conductors are not visible to you because they are behind this panel. Okay. So, what can happen is you can always take a thermal image, and suppose there is some short circuit or some loose connections. So, a lot of heat generation is there. So, by doing a quick thermal imaging scanning of the surface, you can find out what the temperature of this area is and where the short circuit is. Then later on you can do a diagnostic to find out why that short circuit happened. So, thermography is a very quick way of finding hot spots. Okay. Particularly in the cement plant, okay. In paper mills, you can see a lot of hot areas are there in the rolls. Automobile, for example, this brake drum or the rotor has heated, you can see very easily such things. Particularly in electronic circuits, if some particular component is not getting power supply, it would not heat. So, you can see some cold spots, and then you can say perhaps this device, semiconductor device or whatever, this IC chip is dead, because anywhere in a circuit I will have this energy depending on the square of the current, and that will be the heat generation. So, this I can very easily through a thermal imaging in a TV circuit, you can find out whether a semiconductor is not powered. Or defense surveillance, a lot of IR cameras are used for surveillance, okay, finding out hot surfaces. The cops running after a robber, if somebody is running, you can find out the body temperature rise. For example, look at how eluding this temperatures could be, in a coal mine where you have dump. Okay, there are a lot of hot spots. Okay, they are all, you can see slag has been deposited, and then you can see underneath this you have very high temperature. Infrared image, okay, you can find out where there is a cold air conditioning, there is a hot air coming out. Okay. Darker means cooler. So, this image says is the headlights, engine is radiating heat, the heater in the vehicle is running, so that you can see a lot of hot areas. So, these are all very easy areas to find out. Maybe there is not enough heater coming out here, you can find out where the flow is cold and flow is hot. So, maybe this passage is choked. So, very quickly you can find out through thermal imaging. Here in the laboratory, we are doing a thermal imaging to find out the bearings temperature rising because of a misalignment in the shaft. And this is again in the laboratory, wherein the back side of a refrigerator, see this back side, it is a metal, it is a very bad emitter, but this compressor is black and dull on the outside. So, it is a good emitter. So, you can very easily measure the temperature of the compressor, okay, and all the conductors by using a thermal imaging. So, these are some of the applications of thermography for finding out quick ways to find out faults, and more of this you will find in my book. Thank you.